Welcome back to the continuation of Module 4 on the inputs needed to use the PMed software. As a reminder from Module 1 on the course schedule or roadmap, Module 4.4 overviews and discusses the layer properties needed to use the PMed software. Module 4.4.4 focuses on the Portland cement concrete layer material properties, which include the thermal properties, material component and volumetric properties of the concrete mixture, and the engineering response and strength properties of the concrete mixture. There are 4 learning outcomes for Module 4.4.4 on the Portland cement concrete layer properties. The first is to list the PCC layer properties needed for design. The second is to discuss determination of the representative PCC material properties for use in design. The third is to explain the change in the PCC properties over the design life of the pavement structure and how those are considered in the PMed software. The fourth and final learning outcome is to describe the impact and determination of the relationship between strength and elastic modulus and how that relationship is applied and used in the PMed software. Chapter 10 of the MEPDG Manual of Practice is the determination of material properties for new paving materials. Section 10.3 includes a tabulation and discussion on the PCC layer properties and test procedures needed to determine the PCC materials input variables needed for design. This session discusses each of the material properties included in tables 10.4 and 10.5. We'll now go to the Manual of Practice under Chapter 10 and Section 10.3 PCC material mixtures for concrete, lean concrete, and cement-treated base materials. So Section 10.3 includes Table 10.4 as well as Table 10.5. Table 10.4 is a PCC material input, level 1 parameters, and test protocols for new and existing PCC layers. And so Table 10.4 includes the design strategy type, the different measured material properties, the source of the data and whether it's a test procedure and or an estimate, and then the last column is the recommended test protocol and or data source itself. Table 10.5 includes the recommended input parameters and values, limited or where there is no test capabilities for the PCC materials. These basically include input levels 2 and or 3. The first column is the measured property, and then the second column is the recommended input levels or values for levels 2 and or levels 3. So it's recommended and suggested that the designer review these tables in determining the input values to be used to characterize the Portland cement concrete layer properties to be used in design for using input levels 1, 2, and or 3. So we will now return to, to the presentation and continue. A screenshot showing the tabs for the PCC layer properties and input variables are shown on this screen. The PCC General tab is for the volumetric and response properties, and we will show these in terms of the software in just a second. The second tab is the PCC Thermal tab, which includes a listing of the thermal properties. The third tab is the PCC Mixture Properties tab, including the concrete mixture as well as component mix properties and or features of the mix. The fourth and final tab is the PCC Strength tab, which includes the strength and engineering response or elastic modulus properties themselves. The PCC layer properties or input values will be defined later in this module. The software will be used to show where the input variables are located and the input variables with for the different hierarchical input levels. So we'll open the software now and go through the different PCC layer properties. So these are the PCC layer properties. We're going to focus on the jointed plane concrete pavement, but we'll make note in the presentation for the material properties, the concrete material properties that are also required for continuously reinforced concrete pavements. So the first is the PCC General tab. It includes the Poisson's ratio as used for other pavement layers, and then the unit weight of the concrete mix. These are the two input variables under the PCC General tab. The next tab is the PCC Thermal properties, and there are 3 values that are required. The PCC coefficient of thermal expansion, which is a very important property. This property is typically measured or comes from the historical database of the agency for different mixtures and aggregate types, or it can also be selected depending upon the aggregate type from the MEPDG Manual of Practice in tables 10.5 and or table 10.6. The second is the PCC heat capacity value. This is typically the default value that's used, and it's generally recommended that the default value be used, especially if the default was used in the local calibration process. The third is the thermal conductivity of the concrete layer, and this is also typically default value that's used. If the default values were used in calibration, then it's suggested that those same default values be used for the thermal conductivity variable. The third tab is the PCC mixture properties. The first is aggregate type, and different aggregate types are shown here, and they go in the drop-down window, which go from quartzite to limestone down to a chert-type gravel aggregate. So these are the aggregate types that are used. The next is the cementitious material content. This would come from the historical database typical of concrete mixes constructed or specified and or constructed on projects. The third variable is the cement type, and we can have cement types, type 1, 2, or 3. The water-cement ratio is the fourth mixture volumetric property entered by the user. It also will come from the historical database or historical construction database. The next or fifth one is the curing method, which is really a construction variable. And there are two types, either wet curing or use of curing compound. The next input variable under the PCC Mixtures tab is the reversible shrinkage. A typical value or the typical default value is 50%. And we will get into this later in the presentation. The next input variable is the PCC zero stress temperature. It can be entered by the user, or it is typically calculated by the software. Again, depending upon the calibration process, if the PCC zero stress temperature was calculated in the calibration process, then it's generally recommended that its use in design would also be using the regression equation to calculate the variable internally. And if it's measured for calibration, then it should come from the historical database as a measured PCC layer property. But again, in most cases, the PCC zero stress temperature is calculated internally by the software. The next parameter is time to develop 50% of the ultimate shrinkage in days. And again, this is typically a default value, but it could be entered by the user. Again, it should be consistent with how the calibration process. If the default value was used in calibration, then it is suggested that the default value be used in design. The last PCC layer property is the ultimate shrinkage. This can be calculated internally by the software, or it can be measured externally in the laboratory and the value entered by the user. In most cases, the ultimate shrinkage is calculated internally by the software. And we will discuss the ultimate shrinkage test later in the presentation. Again, like many of the other variables, to be consistent with calibration. For calibration, if the ultimate shrinkage was calculated internally, then it is suggested that that internal or ultimate shrinkage to be used in design also be calculated internally by the software. The final tab, or the fourth and final tab, is the PCC strength. And we'll start with input level 1 first. So input level 1 is simply the modulus of rupture and the elastic modulus measured in the laboratory at different days. The typical days in the software are 7 days, 14 days, 28 days, and 90 days. So these, for input level 1, the modulus of rupture and the elastic modulus would be measured in the laboratory at these specific days. In addition, there is a 20-year, 28-day ratio of the modulus of rupture. That can also be determined by the user or the default value used by the program. The other ratio is the 20-year, 28-day ratio of the elastic modulus. Again, this could be the typical default value, but again, like many of the other parameters, if the default values are used or were used in calibration, then it's suggested that those default values be used for design. And if they're determined from measured properties from field experiments for calibration, then they should also be used for design to be consistent and have consistent input properties. So now let's move to input level 2. Input level 2 is basically the same time requirement, 7-day, 14-day, 28-day, and 90-day, but the compressive strength measured in the laboratory is used. The compressive strength is used to then calculate the modulus of rupture at each of these days. In addition, the 20-year, 28-day ratio of compressive strength is also a required input to the PMID software. And a default value of 1.44 is typically used unless it is measured by the agency from historical or research purposes. Again, to ensure input compatibility, if the default ratio has been used for calibration, then it's suggested that that same default value be used for design. Input level 3 is simply entering the strength at 28 days, or only one strength value measured at 28 days. So we can have a strength measurement, the 28-day modulus of rupture, measured in the laboratory, and or the default value used, where the modulus of rupture is measured in the laboratory at 28 days, or the compressive strength can be measured in the laboratory at 28 days, and or determined from default values from regression equations. If the 28-day compressive strength is used, then the program will convert that compressive strength to a modulus of rupture. And the modulus of rupture will be used in the transfer function for predicting pavement distress over time for concrete pavements. The elastic modulus can be either user-defined, where it's measured in the laboratory at 28 days, or it can be calculated from the 28-day compressive strength or the 28-day modulus of rupture. So again, this strength versus elastic modulus will be a very important relationship, and we will discuss this in greater detail in terms of how it is used in the PMID software in the presentation. But again, like for the other parameters, for input compatibility, if we're having the software calculate the elastic modulus during calibration, then the elastic modulus should be calculated by the program for design purposes. And like I said, we'll get into that in a little bit more detail later in the presentation, because that is a very important topic and or parameter. So that ends the where the PCC material properties are entered in these 4 tabs for structural design. So we will go back to the software now and then continue with the presentation from where we left off. So this is a screenshot showing the PCC General tab that we just illustrated in the software. So this will be kind of a duplication of what we just covered from the software in the presentation. So there's 2 properties are included under the PCC Material tab. And these are Poisson's ratio and the unit weight of the mixture themselves. Remember, Poisson's ratio is an engineering response property, but it is included under the PCC General Materials tab, like many of the other produced or constructed materials, as well as for subgrade materials. The next tab is the PCC Thermal. This is a screenshot showing the PCC Thermal tab. There are 3 thermal properties that are included within this tab. The PCC coefficient of thermal expansion, which is very important, and cracking and other distresses are very sensitive to this parameter or input variable. The next is the PCC heat capacity, and then the third is the PCC thermal conductivity. Remember, if the PCC heat capacity and thermal capacity were default values were used in calibration, then for design, the default values are recommended for use. The PCC coefficient of thermal expansion can be measured or determined from the historical construction database of the agency, and or it could be tied to the type of aggregate that's used in design in terms of the default values for different aggregate types that are included in the or explained in the MEPDG Manual of Practice, Table 10.6 that we previously covered. The 4th tab is a screenshot showing the PCC mixture property tab. There's multiple PCC properties that are included under this tab, which are grouped into 4 different input categories. The first will be the material component features, and they include the aggregate type as well as the cement type. And remember, there's 3 different types of cements, type 1, 2, and 3, that we showed in the software from the drop-down screen. And the aggregate type include numerous aggregate types that are included in the drop-down screen that the user can select from. So from after the material component features, we have mixture volumetric properties. And these include the cementitious material content entered by the user and typically comes from the historical concrete database for the agency or maintained by the agency, and the water cement ratio of the specific mixture type selected for design. The next category is the shrinkage properties. The shrinkage properties include reversible shrinkage. The default value is 50%, as we illustrated in the software. The time to develop 50% shrinkage. The default value is 35 days. And then the ultimate shrinkage, which is typically calculated internally by the software. which we illustrated in the software when the software was open. The fourth category are the construction features, which are really not material properties, but they're construction features related. The first is the curing method, and remember there's two: use of curing compound or wet curing, that are included in the drop-down screen. The last is the PCC zero stress temperature. And remember, that is typically calculated internally by the software, but the user should be consistent with how the rigid transfer functions were calibrated in terms of design. So if the PCC zero stress temperature was calculated for calibration, then it's generally recommended that it be calculated by the software for use in design. Input compatibility and consistency or compatibility between calibration and design is very important for the different material properties, including Portland cement concrete. This is the fourth tab, PCC strength, and we'll start with input level 1 for jointed plain concrete pavements. So as we showed in the software, the PCC strength tab for jointed plain concrete pavements for input level 1. For input level 1 properties, this includes the modulus of rupture and elastic modulus measured at different ages. The different ages are 7 days, 14 days, 28 days, and 90 days. The modulus of rupture is measured for at each of these days, and then the elastic modulus is measured for each of those days themselves. In addition, there is a 20-year, 28-day ratio of the modulus of rupture, as well as a 20-year, 28-day ratio of elastic modulus that are required inputs. Input level 1 for continuously reinforced concrete pavements are shown on the following slide. So this is input level 1 for CRCP. It's basically identical or the same as for jointed plain concrete pavements, with one exception, and that is the splitting tensile strength of the concrete mix that's required for CRCP design. So the PCC input variables for CRCP include the modulus of rupture for input level 1 and the elastic modulus measured at the different times or ages shown as 7 days, 14 days, 28 days, and 90 days. The other input level 1 inputs for the PCC strength also include the 20-year, 28-day ratio of the modulus of rupture and the 20-year, 28-day ratio of elastic modulus. And again, the split tensile strength is an additional input value measured at 28 days for CRCP pavements. So this is input level 2 for JPCP and or CRCP. For input level 2, the compressive strength is required at 7 days, 14 days, 28 days, and 90 days. The 20-year, 28-day ratio of compressive strength is also required. These input variables are needed, again, for both JPCP and CRCP. The software estimates or calculates the splitting tensile strength from the compressive strength value at 28 days for input level 2. So the compressive strength is used to calculate. Also, the compressive strength is used to calculate the modulus rupture, because the modulus of rupture is the specific concrete strength value used in the transfer functions to predict pavement distress. For input level 3, only one strength value is needed, and only at 28 days themselves. So the elastic modulus, and that can be either the 28-day modulus of rupture and or the 28-day compressive strength. If the user enters the 28-day PCC compressive strength, then the software will calculate the modulus of rupture from the compressive strength. The elastic modulus can be measured in the lab at 28 days, or the regression equation embedded in the PMED software can be used to calculate the elastic modulus from the modulus of rupture. And these input variables for input level 3 are needed for both JPCP as well as CRCP. And as a reminder, the software estimates or calculates the 28-day split tensile strength from the other strength value entered into the software. The splitting tensile strength is an input value required for CRCP designs. We are going to discuss the importance and application of measuring the 28-day elastic modulus, or letting the software calculate the elastic modulus from the strength values entered using the regression equation embedded in the PMED software later in the presentation, because that becomes a very important relationship, especially if we're using laboratory measured values in comparison to the regression equation embedded in the PMED software. So in summary, the test procedures used to measure the PCC material inputs needed for the PMED software are grouped into 4 overall categories: the engineering response and strength properties, as listed on this slide, the volumetric and shrinkage properties, and the thermal and other properties of the PCC mixture. The test procedures for each PCC property are listed in Table 10-4 in the MEPDG Manual of Practice. Determination of these PCC layer properties will be further discussed in more detail in the next section of this module, because during the structural design, which can be 1 or 2 years prior to construction and or contractor selection, the PCC mixture is unavailable for actual testing in the laboratory for most design projects. The volumetric and shrinkage properties are listed on this slide for the concrete mixture. The test procedures are where the PCC layer input variables are determined, are listed on the slide and in Table 10-4 in the MEPDG Manual of Practice. Remember that many of these properties, like the strength properties, are not available for the specific mixture that's going to be constructed by the contractor, because during structural design, in many cases, the project has yet to be bid and the contractor has yet to be selected. So many of these will come from the agency's historical database itself, rather than specific laboratory measured values for the concrete mixture being constructed for the specific project. So that's an important item to remember, and it also the importance of the material libraries to be developed or used for design. The thermal properties and construction properties are listed on this slide. The test procedures, or where the PCC input variables are determined, are listed on the slide and in Table 10-4 in the MEPDG Manual of Practice. Again, we should be consistent in terms of the use of default values and or regression equation in design to be consistent with how or the values were used or determined in calibration. So there needs to be consistency between design and calibration. As for the other process materials, as we previously mentioned, the structural design is completed prior to the contract being let. The contractor is unknown, and the PCC mixture has not been produced for the specific design project. So the question becomes, where do the PCC material component and mixture properties come from? This is where the agency's materials and construction specification and the historical construction database become important, and is one of the ties between the structural design and construction. For the different PCC mixtures specified by the agency and placed by the contractor, the average values for the PCC material input variables that meet the construction specification should be determined from historical or previous year's construction data that were found to be acceptable. Many agencies from that data have created PCC XML material files or material library files for the concrete mixtures included in their construction specifications. This allows the designer to select a concrete mixture when completing the rigid pavement structural design with confidence. So the importance of these XML material libraries really cannot be overemphasized. This section of the presentation focuses on the volumetric and engineering response properties and the importance of making sure they are compatible. The thermal, shrinkage, and volumetric and other properties or features of the concrete mixture will be briefly discussed in the following slides. Remember from the earlier slide, the values extracted from the concrete mixture design should represent the average values of a specific PCC mixture estimated from the agency's construction materials database. And these are simply the listing of the thermal, volumetric, and shrinkage properties that we've previously discussed. Coefficient of thermal expansion, ultimate shrinkage, time to 50% shrinkage, reversible shrinkage, the air content, the water unit weight, and other construction properties or features, curing, types of curing, and the PCC zero stress temperature variable. Now, the coefficient of thermal expansion is measured in accordance with AASHTO 366. The CTE, or coefficient of thermal expansion, defines the change in the length of the test specimen or PC slab under a change in temperature. The CTE value has an important impact on the tensile stresses calculated at the top and bottom of the slab in terms of the curling of the PCC slab. The temperature gradient through the slab predicted by the enhanced integrated climatic model that we discussed earlier under Module 4 and discussed specifically under Module 4.2 defines whether the tensile stresses from the day or nighttime curling are higher at the top or bottom of the PCC slab. The aggregate type, which is important, and the moisture level at the time of measurement have a significant impact on the CTE value. This slide includes a schematic of the test procedure, AASHTO T336. As the temperature is lowered or increased, or through a temperature cycle, the change in the length of the test specimen is monitored. As a side note, the CTE value originally included in the long-term pavement performance database were in error. The CTE values in the current LTPP database have been corrected and updated. So the current values can be used by the user. For a more detailed description of the test method and outcome, the designer is referred to AASHTO T336. The ultimate or total shrinkage of the PCC slab can be measured in accordance with ASTM C157 and ASTM C490. The total or ultimate shrinkage of the PCC is an input variable that estimates the contraction of the PCC slab due to volumetric contraction caused by a loss of moisture as the slab cures over time. The total shrinkage is an important input that has an impact on the tensile stress at the top and bottom of the PCC slab. The test, however, is not that practical because of the length of time of the test procedure, which is typically 50 days. So the ultimate shrinkage is typically calculated by the regression equation included in the PMED software. The relative humidity, cement type and amount, and the water-cement ratio are variables that impact the total shrinkage. This slide includes a schematic of the test procedure for the shrinkage. As a PCC test specimen loses water, the volumetric contraction of the specimen is monitored. As we discussed previously, the test procedure is not that practical, so the regression equation included in the PMED software is normally used to estimate the total PCC shrinkage. For a more detailed description of the test method and its outcome, the designer is referred to the ASTM test standards, or test procedures C157 and C490. There is no AASHTO test standard for measuring total shrinkage. This graph displays a schematic of the typical behavior of the PCC mixture upon drying and re-wetting to estimate the amount of shrinkage that is reversible. The reversible shrinkage as opposed to irreversible shrinkage. The reversible shrinkage is dependent on or is affected by the relative humidity. The impact of differential shrinkage, or the drying and re-wetting of the PCC, results in moisture warping caused by differential shrinkage throughout the slab. The reversible shrinkage is normally estimated to be about 50% of the total or ultimate shrinkage. The total or ultimate shrinkage. 50% is the default value that is suggested for design for reversible shrinkage. So 50% of the total shrinkage then is the shrinkage that is irreversible and permanent. Unit weight is important to assess the consistency of the PCC mixture and an input to the PMAD software. The fresh concrete is measured in a container of known volume to determine the density and/or unit weight in accordance with AASHTO T121 or ASTM C138. The entrained air content is vital for freestyle durability and needs to be checked prior to placement of the concrete. The entrained air content can be determined in several ways, but is most frequently tested with one of the devices pictured on the slide. The photo in the upper right shows a pressure meter air test. This is the most common used device, but is not appropriate for lightweight or porous aggregates. The photo on the bottom right shows a volumetric air test that can be used for all types of aggregates. Remember from an earlier slide, the values noted from the concrete mixture design should represent the average values of a specific PCC mixture estimated from the agency's construction materials database. The other PCC mixture properties are listed on this slide and are typically project specific. The input variables are also location and mixture specific. These include the cementitious material content, the water cement ratio, cement type, aggregate type, and the curing method that is used. Cement type, aggregate type, curing method are typically project specific, but in many cases the designer will have a good indication on what type are going to be used on the design project. And the volumetric properties can typically come from the agency's historical construction database for concrete mixtures of a specific type or specific specification of concrete mixtures. Again, remember from an earlier slide, the values noted from the concrete mixture design should represent the average values of a specific PCC mixture estimated from the agency's construction materials database. The other PCC material properties. The PCC zero stress temperature, these are material properties not measured, so typically the default values are used. These include the PCC zero stress temperature, which is listed as a material property, while the pavement curl warp effective temperature difference is listed as a PCC design feature. So when we get into Module 5 on discussing rigid pavement design, we will come back to permanent curl warp effective temperature difference. This is not included under the PCC layer properties themselves, but under the design feature of the concrete pavement. However, both are construction features and variables defined during construction. In other words, the PCC zero stress temperature and the permanent curl warp effective temperature difference are project specific. The PCC zero stress temperature is a PCC temperature when the PCC mixture sets. In other words, the temperature at which no tensile stresses occur in the PCC slab without any wheel loads applied to the surface. No curling of the slab occurs. The temperature value is normally calculated using the regression equation in the PCC software, but it can also be entered by the designer. The variables included in the regression equation that impact the PCC zero stress temperature are the mean monthly temperature for the month of construction and the cementitious content of the concrete mixture itself. The permanent curl and warp effective temperature difference is the effective temperature from the bottom to the top of the slab. The default value suggested for use for all climates is a minus 10 degrees Fahrenheit. This value can be changed during calibration, but once it is determined, that value should be used for design. In other words, it can be a parameter used in calibration to reduce bias and or reduce the standard error. Now that we've covered the volumetric, thermal, and shrinkage properties of the concrete mixture from the previous section of this module, now let's focus on the response and strength properties and their relationships of the PCC mixture. The structural properties of the PCC materials or layers include Poisson's ratio, elastic modulus, and the strength of the PCC mixture, which can be the modulus of rupture or the flexural strength, the compressive strength, and as we noted earlier, the split tensile strength is required for CRCP design. The modulus of rupture or the compressive strength are needed for all rigid pavement design strategies. Poisson's ratio has already been defined for other pavement layers and or materials. The PCC Poisson's ratio is required to compute critical pavement responses in the concrete slab. Poisson's ratio is especially important to PCC layers in relation to calculating the tensile stress at the top and bottom of the PCC slab for predicting fatigue cracks or percent slabs cracked for JPCP and the number of punch-outs per lane mile for CRCP. The PCC elastic modulus is a critical property because it has a direct impact on the calculated tensile stress at the bottom and top of the PCC slab for predicting cracking in JPCP and the number of punch-outs in CRCP. The PCC elastic modulus is measured in accordance with ASTM C469, which is a static modulus of elasticity. For pavement evaluation and rehabilitation designs, the elastic modulus can be determined from the falling weight deflectometer or through sonic test methods. The elastic modulus determined from the FWD or sonic or seismic test methods represents a dynamic or rapid loading condition, and there is a systematic difference between the static and rapid loading conditions. The static modulus is about 80% of the elastic modulus determined from rapid loading conditions, or approximately 0.8 of the modulus measured from rapid load applications. A point to remember, the global calibration of the transfer function used the static modulus of elasticity from ASTM 469. So if the PCC modulus of elasticity is determined from rapid loading condition, that value needs to be reduced by multiplying the dynamic value measured from FWD or seismic or sonic means by 0.8 to be compatible with the inputs used in the global calibration process. Again, input compatibility and the consistency between variables used for calibration and those used for design. Those are two very important topics or concepts that we will have been referring to throughout this workshop. This slide includes a short video of the test method and setup for measuring the elastic modulus and Poisson's ratio. This simply shows the concrete cylindrical specimen in place with the LVDTs and or other measurement devices attached to the concrete cylinder. And again, this is in accordance with ASTM C469. The modulus of rupture for PCC mixtures is a critical material strength for predicting the performance and fatigue cracking resistance of rigid pavements and PCC overlays, and is measured in accordance with AASHTO T97 or ASTM C78. As shown in this slide, from the picture and the schematic, the third point loading beam break is used to determine the modulus of rupture. However, the beams are difficult to prepare and handle, and even slight imperfections in the beam can result in significant strength variations. So the compressive strength of cylinders is often measured and used by agencies to estimate the modulus of rupture through a correlation or regression equation between compressive strength and modulus of rupture. As shown in this slide, the beam specimen is loaded at third points, and the beam is loaded at a constant rate of about 125 to 175 pounds per square inch per minute until the beam breaks itself. The beam is the fracture typically initiates in the tension surface within the middle third of the beam span length. This slide includes a short video clip for measuring the flexural beam strength test to measure the modulus of rupture. The center of the specimen, showing the failure, was not possible to be shown because of the test setup, the specific test setup. The PCC modulus of rupture is used to estimate the allowable number of load applications of the PCC layer for predicting fatigue or mid-slab cracking. And we will get into that transfer function, in specific transfer function, in Module 5 on rigid pavement design. The compressive strength of the PCC is specified for virtually all structural application and is commonly used for rigid pavement design as well because of the ease of sample preparation, handling, and testing. However, compressive strength is not used directly within the fatigue cracking prediction model or transfer function. The compressive strength is correlated or used to predict the modulus of rupture, which is used directly to predict cracking and other distresses through the PMED software. This photo shows a PCC test specimen being loaded to failure to assess the unconfined compressive strength. Unconfined compressive strength. The load rate has a significant effect on the strength and is specified in the test protocol. This slide includes a video clip of the compressive strength being measured in the laboratory in accordance with AASHTO T22. As noted in the previous presentation, many agencies specify the minimum compressive strength of the PCC mixture. As we noted earlier, the compressive strength is used to then calculate the modulus of rupture, which is directly used to predict performance and the different distresses in the PMED software. The splitting tensile strength is measured in accordance with AASHTO T198 and or ASTM 496 and is needed for the CRCP design strategy to determine crack spacing. The splitting tensile test is where a compressive force is applied along the diametral axis of a cylindrical specimen at a rate of 100 to 200 psi per minute until failure or cracking of the test specimen occurs. The splitting tensile strength is about 10 to 12% of the compressive strength and about 60 to 70% of the modulus of rupture. Now let's focus on an important understanding of the hierarchical concept within the PMED software for rigid pavement design and concrete properties. This is the relationship between strength and elastic modulus of the concrete mixtures, on whether the default value is used or whether it or measured, whether the elastic modulus is measured in the lab or it's calculated internally by the software. And this is a relationship between the strength and elastic modulus of the concrete mixture. Remember, elastic modulus can be calculated by the software from the strength measured value, which is input level 3, or it can be measured in the laboratory for the designer. So the question becomes, does this have an impact on the predicted distresses? And if so, is that difference significant? This section covers and explains this determination of the PCC strength and response properties of modulus of rupture and elastic modulus. Remember the hierarchical input levels for the PCC modulus of rupture and elastic modulus that were discussed earlier in the module and shown in the software screenshots themselves. The PCC modulus of rupture is the value used in the PMED software to determine the allowable number of load repetitions for estimating fatigue damage and other distresses. The modulus of rupture can be calculated from the compressive strength using the regression equation in the PMED software, or it can be measured in the laboratory at different ages. The PCC elastic modulus is the response variable used by the PMED software to determine the tensile stresses at the top and bottom of the PCC slab for estimating the fatigue damage and other distresses from wheel loads. The elastic modulus can be calculated from the modulus of rupture using the regression equation in the PMED software, or it can be measured in the laboratory at different ages. The following slides will display the regression equations that are included in the PMED software. This is the regression equation included in the PMED software for estimating the modulus of rupture from the compressive strength or input level 2. The regression equation is included in the Manual of Practice, section 10.3 of chapter 10. This is the regression equation included in the PMED software for estimating the elastic modulus from the compressive strength and density of the PCC mixture. The regression equation is included in the Manual of Practice, section 10.3 of chapter 10. We just covered and explained the different response and strength properties that are needed to use the PMED software for rigid pavement design. In addition, we reviewed the different hierarchical input levels for PCC regarding strength and elastic modulus. There is a relationship between strength and elastic modulus, so elastic modulus can be calculated from one of the strength measurements for input level 3. However, elastic modulus can also be entered by the user from laboratory measured values. So the question becomes, or is, as noted at the start of this section, can the calculated values be intermixed with the laboratory measured values? And we will discuss that important answer to the question in the following slides. Remember, hierarchical input levels for PCC strength and elastic modulus. Can they be intermixed? In other words, does it matter or make a difference if flexural strength is measured or calculated from the compressive strength? And does it make a difference if the elastic modulus is measured or calculated from a strength measurement? The answer to this question is the user needs to be careful about intermixing strength and elastic modulus values and base their decision or the answer to that question on their own laboratory measured values. This will be explained in the next slide. So, the answer to the question on the previous slide, does it make a difference, is yes, it can. This graph displayed on this slide includes a relationship between the 28-day modulus of rupture and average 28-day elastic modulus that is included in the PCC software as displayed by the solid black line. So the solid black line represents the relationship within the PMED software between the average 28-day modulus of rupture and average 28-day elastic modulus. The data points displayed in the graph are actual values measured in the laboratory for a range of PCC mixtures used by an agency. As displayed, there is a consistent difference or bias between the two, between the regression equation and the actual laboratory measured value. So, there can be a bias or a consistent difference between the regression equation in the PMED software and the actual laboratory measured values produced from the agency's construction and mixture specifications. Elastic modulus and modulus of rupture both have a significant impact on the fatigue cracks predicted by the PMED software for rigid pavement design, as well as the number of punch-outs for CRCP pavements. So there will be a difference between the two input levels as displayed on this graph. So there can be a bias between the input levels for concrete mixtures. Since there can be a bias between the input levels and how the PCC properties are determined, the user or designer needs to be careful about intermixing strength and elastic modulus values measured in the laboratory as opposed to using the regression equation. Another question is, what input level should be used? In answer to that question, the user or designer needs to base their decision on their own laboratory measured values and correlation between the laboratory measured strength values and laboratory measured elastic modulus values. In other words, the designer should use the hierarchical input level that is consistent with how the rigid pavement transfer functions were calibrated or how the calibration coefficients were derived. And this will be explained in the next slide. And this topic will also be discussed again and in more detail in Module 5 on rigid pavement design. So the designer or user needs to determine first if there is a difference between the regression equation, PMED regression equation, and their actual laboratory value from their construction database. If there is no bias, then input levels 1, 2, and 3 can be intermixed. If there is a bias, as shown on this slide, the input values between input levels 1, 2, or 3 should not be intermixed. And whatever was used in calibration should also be used in design. This slide is basically a review of some of the information presented in the PCC inputs module because of the interrelationship between strength and modulus and its importance in predicting different distresses of rigid pavement. So some questions are, what is the impact on cracking if the PCC strength increases and the elastic modulus does not change? In other words, only the flexural and or compressive strength increases and the elastic modulus remains the same. So the elastic modulus remains the same and the average 28-day modulus of rupture or average 28-day compressive strength increases for the same modulus. As the strength increases with no change in modulus, there will be an increase in performance or a reduction in mid-slab cracks for JPCP, and a reduction in punch-outs for CRCP. Simply because as the concrete mix is getting stronger, the number of allowable load applications is increasing, and since the elastic modulus is not changing, the tensile stresses computed at the top and bottom of the slab will basically be unchanged because there is no change in the elastic modulus. So, what is the impact on cracking if the PCC elastic modulus increases and the strength does not change? In other words, we're not changing the strength for different mixes, but the elastic modulus is increasing. So strength is remaining constant, elastic modulus is increasing. As the elastic modulus increases with no change in strength, the stress in the slab increases. Without an increase in the PCC strength, the performance will decrease, or the amount of cracking and punch-outs will increase. What is the impact on cracking if the elastic modulus and strength of the PCC mixture increases? So, as the strength increases and the elastic modulus increases, what is the impact on cracking? As the elastic modulus increases and strength increases, in other words, following one of these lines, the impact of cracking may increase or may decrease. It really depends on how the strength increases relative to the increase in elastic modulus as displayed on this graph. So if the elastic modulus is increasing at a much faster rate than the strength, it is likely that cracking will increase. However, if the strength is increasing at a faster rate than the elastic modulus, it is likely that cracking may decrease. So it's going to depend on the rate of increase of the modulus and strength of the mix. So what is the impact on cracking if the coefficient of thermal expansion increases? And as the CTE value increases, the amount of cracking and faulting will also increase, because the slab will exhibit a greater change in length with temperature changes throughout the slab. So greater tensile or greater stresses at the top and bottom of the slab, and so potentially greater amounts of cracking, assuming a constant strength and constant elastic modulus. So now let's focus on the important topic to understand how the PCC properties can change over time as simulated or considered within the PMED software, the time-dependent properties. It is common knowledge that the elastic modulus, modulus of rupture, and flexural strength and compressive strength of the concrete mixture will increase over time. The PMED software does include a growth function to estimate the increase of these properties, all three properties, over time, which are taken into account for predicting the different distresses of the rigid pavement design, both for JPCP and CRCP. This slide includes a graphical illustration of the increase or growth in the elastic modulus and flexural or compressive strength of the PCC mixture. The data sources used for this growth function or for model development were extracted from the LTPP SBS2 experiment, from which over 470 test results were available for use, the long-term Portland Cement Association study conducted by Wood that included 210 tests, and the actual road test, which included 15 tests or mixtures. The growth function embedded in the PMED software considers the curling method, the loading method, and the cement type used in the concrete mixture. All of those do have an impact on the growth function. And also the growth function is also identified in the MEPDG manual of practice. If the designer or user only has a 28-day strength and or elastic modulus for input level 3, the strength and elastic modulus values are calculated from the growth function over the age of the PCC layer and used in the response and distress computation at different ages throughout the design period, whether that's 20 years, 30 years, 40 years, or whatever the design age is, or the design life is. Similarly, if the designer or user has access to input levels 1 or 2, where the strength and or elastic modulus value have been measured at different ages, like 7 days, 14 days, 28 days, and 90 days, those values are used to develop the growth function for that specific concrete mixture. Those values are used to estimate the coefficients of the growth function, and those are used in calculating the strength and elastic modulus values over time. The PMED software also includes the ratio of the 20-year, 28-day compressive strength, flexural strength, and modulus of elasticity that is used in calculating the values over the design period for rigid pavement design. So not only the time dependent, the 7, 14, 28-day, and 90-day strength, but the 20-year to 28-day strength and elastic modulus value ratios are used in predicting that growth of those strength engineering response values throughout the design period. So now let's do a review or summary of the PCC layer inputs and outcome from this module relative to the PMED software. In summary, the test procedures used to measure the PCC engineering response and strength properties are listed on this slide. The test procedures are also listed in Table 10.4 or 10-4 in the MEPDG Manual of Practice. In summary, the default and or test procedure used to measure the PCC thermal and volumetric properties are listed on this slide. The test procedures are listed in Table 10-4 in the MEPDG Manual of Practice. In summary, the defaults and or test procedures used to measure or estimate the shrinkage properties are listed on this slide. The test procedures are listed in Table 10-4 in the MEPDG Manual of Practice. In summary, the default values and where the component mixture properties are extracted from for the component mixture concrete properties needed for the PMED software are listed on this slide. The component mixture properties are also listed in Table 10-4 in the MEPDG Manual of Practice. Remember, the PCC layer properties entered in the PMED software represent average values for the specific or specified PCC mixture that meet the construction specifications and are determined or were determined from historical or previous year's construction data of concrete mixtures that were found to be acceptable. XML files are typically prepared or can be prepared for the common concrete mixtures used for both JP, CP, and CRCP design. And it is suggested that the XML material library files be prepared by agencies for use in structural design. This makes the design process simpler and also reduces the probability for blunders in entering the concrete data or input values to be used for specific designs. In summary, there were 4 learning outcomes for Module 4.4.4 on the PCC layer inputs. The first is we listed the PCC layer properties needed for structural design. The second, we discussed determination of the representative PCC material properties to be used in design, which, remember, are the average properties and not some reliability or probability property as used in some procedures. They represent the average material properties. The third is we explained the change in the PCC properties over the design life of the concrete pavement. And the fourth and last is we describe the importance of the relationship between strength and elastic modulus regarding rigid pavement design and whether the laboratory measured values can be intermixed with the values used through the regression equations embedded in the PMED software. We will discuss that relationship and the importance of that relationship again when we get into Module 5 for rigid pavement design, both jointed plain concrete pavement and continuously reinforced concrete pavements. So this ends Module 4.4.4. The next module of the training course or workshop sequencing is Module 4.4.5 on asphalt layer inputs.